This is the first in a series of videos about entropy. In this first video, we're going to talk about what entropy is and how we can understand it using probability of different microstates. And in the next video, we'll talk about high entropy conditions. So entropy is represented by the letter S. And this is going to be another force that helps us explain some of the questions that we used a little hand-wavy explanation in the past. So one of these questions from a few lectures ago was about an endothermic reaction. Endothermic, indicating that the enthalpy, which is H, not to be confused with entropy, which is S, that the enthalpy was positive. So how could an endothermic reaction with positive enthalpy, how could this occur spontaneously? That was our question. So here is the page from a previous video where we talked about it. We were talking about the enthalpy of dissolution. We said there are 3 steps to dissolution. There's spreading out the solute, spreading out the solvent, and there is mixing the 2 of them together. We said that 2 of those steps were endothermic and 1 of them was exothermic. And when we added them together, the final total, delta H total, could be exothermic or endothermic. And we said exothermic, that's fine, that's a favorable reaction total, and this would definitely happen, but we said, why would an endothermic reaction happen? And we use this sort of like hand-wavy explanation down here, and we said they can still occur when they increase the system disorder. So that is entropy. So when this force, when the enthalpy is unfavorable and doesn't lead to spontaneous reaction, there is another energetic driving force that can determine whether something is spontaneous or not. So it's determined by a combination of the enthalpy and the entropy. So let's give entropy a proper definition. So the proper definition for entropy, we'll have to be careful about that. Proper definition for S is a measure of the dispersal of energy. And that's per unit temperature. Dispersal of energy per unit temperature. And if you took chemistry in high school, the way you probably learned about entropy was you learned that it was a measure of disorder. This is how we talk about it. We say something that's very disordered has a high entropy, like having a messy room that has a high entropy, and something that has low disorder that is very organized, like a clean room, that would have low entropy. So there's another way that we can talk about entropy, and that is by looking at the statistics of where each of the particles could be to measure how disordered it is. So we can think of entropy as the number of microstates that are possible for a system. Okay, so this is a new word here, microstates. So let's dive a little deeper into microstates. Microstates are just what they sound like. A microstate is one possible arrangement of all of the particles in a system. You can think of this as your messy bedroom. So one possible arrangement would be all the clothes on the bed. Another possible arrangement is all the clothes under the bed. Another possible arrangement is all the clothes on the floor, or half the clothes on the floor and half on the bed. You get the idea. So each distinct possible arrangement of the different items is a different microstate. And the more microstates we have, the higher the entropy. So let's do an example that looks a little bit more like chemistry. So let's say that I have this box, And then I divided it into two equal-sized quadrants. Please excuse my slightly inaccurate drawing skills. So two equally sized quadrants, and let's say we have one particle that we want to put in here. What are the possible microstates for that one particle in these two boxes? There should be two, right? So one possible arrangement is that our particle is here in the left box. And the other possible arrangement is that our particle is here in the right box. So each of these pictures represents one microstate, one possible arrangement of the particles. And in most systems, we have more than one particle. We have significantly more. So what we can say is we can use a formula to calculate the total number of microstates possible for a system. And this one will be pretty easy since it's a pretty small system. So the formula here is n to the x power. So it's an exponential. So our n, that one is the total number of positions. So in this case, we had 2 positions, so our n would be 2. And for x, x represents the number of molecules, or the number of particles. Okay. So and the number of particles in this system was 1. So the total number of microstates possible was 2 to the first. So let's put that down here. So we had 2 possible locations. We had 1 particle in the system. 2 to the first is 2 total possible microstates. And what I'm going to do is I'm going to make a plot and show the distribution of microstates. So I had 1 microstate where the particle was in the left box. And I had 1 microstate where the particle was in the right box. 1 and 1. And I can kind of draw a parabola-shaped distribution over those as to what that kind of looks like. Right now, it doesn't really look like a parabola, but as we add more particles, we will. Okay, so that's a very simple example about 1 particle in several quadrants. So let's increase the number of particles and let's see if we can make that distribution look more like a bell curve like we know in our hearts that it should. So let's say we have 2 particles. So over here, we're going to do 2 possible positions, same as before, but we're going to put in 2 particles. So 2 to the second, 2 times 2 is 4 microstates. So let's try and think about what those might look like. So the first obvious one is that both of the particles would be on the left side of the box. And then we have the equivalent one, both particles on the right side of the box. So these are all the particles on one side are all on the other, but we also can split the particles so that they're in different boxes. So let's draw domino pictures for those. So one option is we could have the red particle on the left and the black particle on the right. Hope you can tell the difference between those colors. And another option is to have the black particle on the left and the red particle on the right. So I know what you're thinking in your head. These are the same thing. There's 1 particle in each box, but if you look at the picture of the domino is not the same. It matters which particle we have on which side. So there's 2 possible microstates for the 1 on one side, 1 on the other side orientation. So if we make a little bar graph for these different states, we're going to have one way to have all the particles on the left side. We have 2 ways to have 1 particle on one side and 1 on the other. And we have 1 way to have all of the particles on the right. And if we draw a distribution for that setup, you can see it looks a little bit more like a parabola. We're feeling better about that. And if we add up the total number of pictures we drew, 1, 2, 3, 4, that equals our total number of microstates. And we can already start to see that the bar in the center, the one where the particles are more evenly distributed, is starting to become the tallest bar. So let's do another one. Let's do 3 particles. So we have 2 possible locations, left and right. We have 3 particles. So 2 times 2 times 2 is 8 microstates. So let's see if we can draw the pictures for those 8 microstates and not get them mixed up with our previous pictures here. Okay, so our first one on the left, we know is going to be all the particles on one side. Ooh, that's kind of a small box. All right, so we're going to have the red particle, the black particle, and we're going to add a green one. So are all the particles on the left side? Sorry for how small looking that is. We'll do better. We know the opposite is going to be true. We know we have one option where all the particles are on the right side. Okay, and then we know we can distribute these. So our options are going to be 3 and 0, 2 and 1, or 1 and 2. So let's try drawing the next set. So let's say we have 2 particles in the left side. So we'll move the red particle to the right, and we'll keep black and green on the left side. And then we can do that same thing for each of the different particles. Red, green, and black can each be the only particle on the right. So there's going to be one orientation with the black particle as the only one on the right. And there's going to be one orientation with the green particle as the only one on the right. Okay, so all of these orientations have 2 on the left side and 1 on the right side, but they're all different because there's a different particle that we put on each side, red, green, or black. So those are all going to be one column. And then we can draw similar pictures for 1 on the left side and 2 on the right side. So we could have red particle be the only one on the left. We could have the black particle be the only one on the left. Or we could have the green particle be the only one on the left. So there are 3 possible ways to have 1 on the left and 2 on the right. Okay, so let's draw a bar graph for those different states. So we've got one way to have 3 and 0. We've got 3 ways to have 2 and 1. We've got 3 ways to have 1 and 2. And we've got 1 way to have 0 and 3. And our parabola is going to make our picture kind of messy, but there it is. 1, 3, 3, 1. And we can see that the middle is getting taller and the sides are getting shorter. And our total 1, 2, 3, 4, 5, 6, 7, 8 equals our total number of microstates. So these pictures are quickly getting more and more complicated. So I'm going to have you do this one on your own. So if we have 2 possible states and 4 particles, 2 to the 4th is going to be 16 microstates. So if you're working with me at home, pause the video right here and see if you can draw 16 different domino pictures for 4 particles. I will wait. Okay, if you're still with me, that means you've either drawn the pictures or you've given up. And I am not going to draw the pictures because they're clearly not going to fit here. But we can draw the bar graph there's going to be one option with 4 and 0. 3, 4. There's going to be 4 options for 3 and 1. There are going to be 6 options, huge bar in our bar graph. 6 options for 2 and 2, where the particles are evenly distributed. Then it's going to look the same on the other side. There's 4 options of 1 and 3. And there's 1 option of 0 and 4. And our parabola is going to be beautiful because I don't have any domino pictures in this diagram. There we are. So the more particles we add, the more parabola-shaped our distribution is going to look, and the taller that bar in the middle is going to be. So that leads us to one of the important parts of this microstate examination. Remember, the number of microstates is related to the entropy, and what we've learned here is that the most probable arrangement of the particles right? The most probable is the tallest bar, the one with the most number of possible ways to make that situation. The most probable arrangement is the most evenly dispersed option. This is important. This is an important part of why we did all these domino pictures. And that tells us that these pictures where the particles are about even numbers in all parts of the container, that's going to have the highest entropy. That's where entropy is going to lead us. So if we were talking about your bedroom, the most probable arrangement would be one piece of clothing covering the entire floor at a depth of one piece of clothing and height. So equally distributed across the entire room is going to be the most energetically favorable arrangement. So in the next video, we'll talk about what sorts of situations have the highest possible entropy.